Here is how to write equilibrium constant expressions. These will be very important for when we move on to doing calculations. And there's a few examples that I've written of reactions. The first one is making ammonia from nitrogen and hydrogen gas. The second one is the acetic acid equilibrium with water to make the acetate ion and H+. And then the third is when the so-called insoluble salt silver chloride actually does dissolve a little bit and make silver ions in solution and chloride ions in solution. So each one of these has been chosen to illustrate a particular aspect of writing an equilibrium constant expression. Now, before I did indicate that we choose products over reactants, but what do we do when we have two of those products and several reactants? And what do we do when we have things that are liquid or solid or aqueous or gases? All of these things are very important to consider and affect how we write the equilibrium constant expression. So let's look at the first equation. We have nitrogen plus 3 hydrogen gases, well, both gases, going to 2 ammonia gases. Now this is a balanced equation. And here's how we would write the equilibrium constant expression. We would say K equals concentration of ammonia on top, because that's product, and then we raise it to the power of the stoichiometric factor, so this gets squared. And then we divide by the reactants. There's a 1 in front of the nitrogen, so there's a 1 right there. And then hydrogen, there's 3 hydrogens, so we're going to raise that to the third power. And this would be the equilibrium constant expression for this reaction. Now, notice how, again, we raise it to the power of the stoichiometric factor, and we use products over reactants. All of these are multiplied by each other, so it's ammonia concentration squared divided by nitrogen concentration times hydrogen concentration to the third power. All of this down here gets included on the denominator, products on the numerator. Now, let's look at what happens when we have aqueous and liquids in this solution. In this case, we're going to look at water, right? Now, water is the solvent, right? There's a lot of it in the solution. And so solvents do not get included in the equilibrium constant expression. So when we write this down, we ignore this part because it's a liquid and it's the solvent. So it does not go in. So when we write this down, we're only going to include the aqueous parts and not the liquid right here. So this one is K, and in particular this one is the K of an acid reacting with water, so it has a special name called Ka. It's just a different K. It's just K with a special name to say, oh, that was an acid. So not too special. So products again. times H3O plus, that's aqueous, all over reactants. And again, we ignore the water, we only put this in. So and we're done, since all of these are, it's all 1 to 1 to 1. Now, if we come down here to the silver chloride equilibrium, this one also has a special name. It's called KSP, which just stands for solubility product. And you'll see why they call it that. You can see why they call it solubility, because this is a solid that is dissolving. So that particular K will tell us how soluble is that salt. And you'll see why they call it a product in just a second. But again, it's still just K, and it's still products over reactants, and it's just another name. So don't get caught up with Ka, Kb, KSP. Kb is for bases. Ka is for acids, and KSP is for things dissolving. Now, does anybody know what the concentration of a solid is? Well, I don't know either. In fact, those don't go in the equilibrium constant expression either. It's really liquids and solids. The solvent or just a solid does not go in. And so in this case, the equilibrium constant expression is just the silver concentration times the chloride ion concentration, divided by, well, there's only one reactant and it's a solid and it doesn't go in. So that's why they call it solubility product, because it's only multiplying. And so solubility product. That's why. So that's a little bit about the equilibrium constant. Now, your book will probably go into a little bit about Kp or Kc. And Kp is just when we use pressures instead of concentration. So we could do that up here with everything being a gas, and we could just say partial pressure of ammonia squared divided by partial pressure of nitrogen, also divided by partial pressure of hydrogen to the third power. Just replace all of these concentrations with pressures. There are times when that particular value is different than the one where we put concentrations in everywhere. But I just tend to focus on the concentration equilibrium constant expression, largely because most of what we do in our laboratory is just concentrations. And we're usually not doing labs where there's a lot of manipulation of just gases. And so it's a little less common to see that. I imagine that if you were a chemical engineer, you may deal with it more. But as a chemist, it's good to be aware that that is a different value. And in some cases, it will be a different numerical value, and it could change based on which pressure units you're using. But just be aware of that. While we're on units, by the way, whenever we talk about concentrations here, we mean molarity. That's what it is, moles per liter, molarity. So that is how to write equilibrium constants, and pretty much every scenario that you would need. So remembering the stoichiometric ratios, put those as the powers, make sure you're using multiplication, make sure the products are divided by the reactants, make sure that you include gases and aqueous or dissolved species in the equilibrium constant expression, and make sure that you do not include solvents or solids in the equilibrium constant expression.